Hello, everyone. I am Diksha Sinha, a graduate student at the Operations Research Center at MIT. And today I'm going to be talking about our work on optimizing offer sets in sublinear time. This is joint work with my advisor Vivek and collaborator Andrew. Now, personalized offer sets, that is personalized recommendations, have become ubiquitous on online platforms today. These are just a couple of examples from personalized recommendations on CNN.com, on Instacart.com, and I'm sure you have come across many more in your own personal experience. Now, having good recommendations is not just nice to haves for these companies, but in fact are deeply tied to their revenues. Now, the way companies think about making recommendation today is really in two steps. The first step is this learning step of estimating a predictive model using past data. The second step is this optimization step, where they use this predictive model to make a recommendation decision from this large number of products that they have and in real time. So I would like to emphasize on two aspects of the problem over here. That first of all, the number of products that some of these platforms have is extremely large. And secondly, this decision of what products to display has to be made in real time. A study by Akamai shows that 100 millisecond delay in loading a page can cause up to 7% drop in conversions. Now, given this large size of products and the strict time requirement, even linear time algorithms will not be able to satisfy our requirement. And thus we need algorithms which are sublinear in the number of products for making this recommendation decision. Now, let me give some more overview of how each of these two steps are run today. So the learning step, in this learning step, both so embeddings are learned both for products and users onto some space. So typically the d-dimensional Euclidean space. And then the idea that these embeddings try to capture is that products which are liked by a user are close to the user in this embedding space. Now, this step really has attracted a lot of attention both from academics and practitioners, and there exists a set of multiple mature algorithms to actually do this step. Now, the second step, which is the optimization step, has not garnered as much attention. Now, so let me tell you what is common in practice today. So after the user and product embedding has been learned, the recommendation is made by returning the products which are near to the user embedding. So again, very intuitive. This was what the embedding was trying to capture in the first place. And the reason this can be done in real time is that these queries of this nature that you find the near neighbors of the user can be run in sublinear time. But of course, we have come across multiple limitations in our own personal experiences. And like this is just a sample of that. So today morning, I logged on to Amazon.com, and this is the set of products that they recommended to me. Now, as you can see, all of these products are just different varieties of the same item, that is a soap dispenser. So this is really a limitation that many similar kind of items are being recommended. And at the heart of it is the fact that diversity in a user behavior is not being accounted for. So Amazon is completely ignoring the other items that I have looked at in the past and making the recommendation solely based on one aspect of my behavior. And the reason this is common in practice today is that real-time optimization is challenging with more sophisticated user models. Now, this is exactly the gap we try to bridge. That is, we propose a sublinear time recommendation algorithm for a richer class of user models, which incorporate uncertainty in user behavior. So let me go and talk about the model. So as I mentioned, we think about the user as having uncertainty. So the user itself is modeled as a random vector. And for the purpose of this talk, I will take that to be on the unit ball. Now, again, the idea behind having randomness in the user is that the platform might not know today what the user is interested in. And you have seen what in the past at different times the user has been interested in. And so today the user can be interested in any one of those things. Hence the user vector is random. Now, since we're talking about personalized recommendations, we can just focus on one user for the purpose of our optimization. And let's refer to that user as user U. Now we have a set of items in our universe, which is again has embeddings v1 through vn in the same d-dimensional unit ball. Then there is a reward function, which is really the metric that the platform is interested in optimizing over. So say something like the engagement or the conversion probability. Then we have a restriction on the number of products that the platform can display to the customer. Now, so with all this, the goal of the platform is really to find the set of products to display to the customer, which really maximizes the expected reward from that customer. Now, the expectation here is over the randomness in the user vector. Now, without loss of generality, we can actually take this user vector as being, instead of being arbitrarily distributed, to being uniformly distributed over m IID samples from this user distribution. And we show this result rigorously in our paper that with only a few samples from the user vector, you will not incur much loss in optimality by instead optimizing over this uniform distribution. So for the rest of the talk, I'll just focus on substituting the user distribution with this uniform distribution on points U1 through UM. Now we make some assumptions on what are requirements from different aspects of our model. So first of all, the reward function itself should be increasing, and in particular, it should be monotone and submodular. Again, both of these are very intuitive characteristics. So monotone, that is, when you increase the number of products that you're offering, you should typically get a larger reward. And the reward also has diminishing returns as more and more products are added. Then the second assumption is that the embedding itself should be a good embedding. And this is, again, this is intuitively, this is the idea of creating behind the embeddings, but we just put it mathematically and say that the distance between the item and the user in this space should capture the reward that the user gets from this item. So that's to say that the reward that the user gets from this item is some decreasing function of the distance between the user and the item. Now, there are some very common reward functions, very common optimization functions, which would fit into this category, that is, which would satisfy these assumptions. The first one is conversion probability under any random utility choice model, in fact, satisfies these two assumptions, when the mean utility itself is a decreasing function of the distance between the user and the product. And then the average revenue under the mixture of multinomial logit model, when the price of products are similar to each other, also satisfies this assumption. Now, further, we make another technical assumption in the paper, which I will not go into much detail right now. So now we have a submodular maximization problem. Of course, the obvious approach to deal with this problem is the greedy algorithm. Now, the greedy algorithm in each step will just try to find the product which maximizes the revenue by adding this one product. And we know that the greedy algorithm gives a guarantee of 1 minus 1 over e times opt. And in the space of polynomial time algorithms, this is the best guarantee that can be achieved. But the challenge with the greedy algorithm is that you have to maximize over all the products. Again, this means that the algorithm will run in time, which is linear in the number of products. So now the question really becomes is, can we approximate this opt value in time which is sublinear in the number of products? So we propose an algorithm called the locality sensitive sampling. And so let me break it into two steps and describe each of these steps. So the first step really is, instead of doing the greedy algorithm on all set of products, can we do greedy over a small subset of good products, which should guarantee that we don't take much time to run greedy. And then since it is a good subset of products, we will get close to the optimal value. Now, what is a good subset of products? So one example is, the optimal set itself, S star. But of course, this is a good subset of products, but we don't know it beforehand. Another natural candidate for this is that if we create a subset of products by sampling each product with probability which is proportional to the reward that the product has for the user, then we are likely to include products which have high reward and then less likely to include products which have low reward. So in fact, we formalize this notion in our paper and we show that the optimality loss is small if each product is sampled with the probability at least 0.5 times the reward that the user gets from it. And so if you construct a subset of products by sampling each product in this manner, and optimize only over that by running greedy, then the optimality loss is small. So then what we really have done is we have shifted the computational burden from this greedy step to the sampling step, where we actually create this small subset of products. And of course, if we were to do naive sampling, it would take linear time. So naive sampling, I mean that we go to each product and draw a Bernoulli sample with its reward as being the mean of the Bernoulli distribution. Of course, that would take linear time. So the way we resolve this issue is that we construct a data structure, and the data structure itself is constructed offline, but the data structure can be queried in real time. That is when a user arrives on the platform. And it will return each of the products with probability, which is proportional to the reward that the user gets from that product. Now, we show in the paper that such a data structure exists, and it can be queried in sublinear time. Now, let me try to give some intuition on how we construct this data structure. And the key part of this data structure is actually using approximate near neighbor queries, which we know can be done in sublinear time. So we want to sample from this distribution, and we said we can sample, approximately from this distribution. Now, what are exact nearest neighbors? So the idea of exact near neighbors is that you return each product which is within a distance gamma with probability 1, and then any product which is farther away, you return with probability 0. Now, approximate near neighbors just generalize this idea and say that you return any product which is within distance gamma with a high enough probability, and return rest of the products with probability which is less than 1 over n. And like decades of research in this field of approximate near neighbors has established that this can be done in sublinear time. So we generalize using this approximate near neighbor data structures to be able to sample arbitrarily from any decreasing function. So you can look at this picture, and what we're exactly doing is stacking a bunch of these approximate near neighbor objects with different heights and widths so that we can imitate any decreasing function. And the key result over here is that we can do this only with logarithmic increase in running time of the algorithm. So, just putting it all together, the algorithm stands as that you create the small subset of products using the data structure that we propose, and then run greedy algorithm over the small subset of products. And the result we have for the performance of this algorithm is that it achieves very close to 1 minus 1 over e times d opt, which is the best known polynomial time guarantee. And this has runtime sublinear in the number of products. This is exactly the goal we had set forth for ourselves. Okay, now let me quickly describe some experiments that we did, both to validate the accuracy of the model and to check the performance of the optimization algorithm. So for this, we used a large data set from a content delivery platform, Outbrain. Now the data set contains information on page views of the users of around 175,000 unique pages and 640,000 unique users. Now we constructed page embeddings from this in the 50-dimensional unit ball. Now in the first experiment, what we really tried to capture is our model, which is more nuanced than existing models, adding value, adding any value in predicting user behavior on online platforms today. So for this, we modeled the user as being uniformly distributed over the pages they viewed in the training data. And for benchmark, we took as just modeling the user as a single point, either as a last viewed page or a mean of all those pages. And essentially, we used both these models to predict the user behavior. And we saw that the mixed model that we proposed actually has much better prediction power in terms of explaining user behavior. Now, the second set of experiment, what we did was we wanted to check what is the value of optimization over this mixed model. So we fixed the mixed model to be the ground truth model. And then we have our algorithm, and we took two other benchmark algorithms, which are common in practice today, that is just recommending approximate near neighbors of the last viewed page or the mean of the first 10 pages that the user saw. And for using each of these algorithms, we obtain a set of 10 recommended pages. And using the ground truth model, we calculated what is the conversion probability under each of these models. So the mean model performs slightly better than the last viewed model, but the LSS algorithm that we propose in this paper beats both of these and has conversion probability significantly higher than both of these benchmark algorithms. So thus we have come up with a tractable algorithm for doing recommendations in sublinear time and which performs well on empirical data. Thank you.